Hello and welcome to this Core Pure Maths video on solving linear equations. So we know how to find an inverse of a matrix, and we're going to use that to solve systems of linear equations. If I've got this system of equations here, 2x plus 3y plus z equals 5, and so on here, we can rewrite that as a matrix, because if I take the coefficients of x, y and z, 2, 3 and 1, 3 minus 2 and 2, 1 minus 1 and 1, and write x, y, z here. If you imagine multiplying this out, you'd have 2x plus 3y plus z equals 5. So that's the first equation there. Then you'd have 3x minus 2y plus 2z is equal to minus 5. X minus y plus z is minus 2. So we can go from this system of equations to this matrix multiplication here. Now, if the inverse of this matrix exists, we can reasonably quickly, find the solution to this set of equations. So the way that we do that, we're going to do it in this example here. Now, the wording of this example is slightly different. This says this point has been transformed by this matrix. So when we transform a point by a matrix, we just multiply the point by the matrix. So this is equivalent to this question here. Use the inverse matrix to find x, y, and z. So you put this matrix M into your calculator and you find M inverse. So we've got M inverse, we find M inverse, and we then multiply that by x, y, z. And that is going to give us, we multiply that by the answer we got there, 5 minus 5 minus 2, and that will give us x, y, and z. And the reason for that is that if we think we had m times x, y, z equals 5 minus 5 minus 2, if we pre-multiply by m inverse on both of this side of this equation, this is the identity matrix. So we've got the identity matrix times x, y, z gives me m inverse multiplied by 5 minus 5, 2. You find m inverse using your calculator. Okay, do not find m inverse manually, otherwise you'll run out of time if you're in an exam. So if we find that using the calculator, then you will get the following matrix. Just check I'm reading my writing correctly. So we get here 0, 1 minus 2, 0.25, minus 0.25, 0.25, 0.25, minus 1.25, 3.25. You multiply that, and again, use your calculator to do the multiplication, but write it all down. You need to show that you found the inverse there. And when you multiply that, you get minus 1, 2, 1. It's important you actually give the solution here. X is minus 1, y is 2, z is 1. If you have time, it's always a good idea to check that these solutions do actually match the equations there. So you would substitute back in to find the answers. So that's how you can use an inverse matrix, particularly on a 3 by 3 set of equations, to find the solution. Now let's think what this means geometrically. If we have got, and we're going to look in 2 dimensions to start with. If we've got 2 simultaneous equations here, there are 3 things that can happen. Either the 2 lines might cross at a point. Think your graph, they might look like that. Or the 2 lines are parallel. So that would be a graph like this. These 2 lines are parallel and they don't meet. So this system of equations is inconsistent. There is no solution to it. Or you might have a system where there's one line and the other line is actually that same line. In which case, there are solutions but there's an infinite number of them. So this system is consistent, but it doesn't have a single solution. So these equations here are just in 2 dimensions. And you could have done this at GCSE. Solve the following system of equations. But what I want to do is think about how you're solving them. Think about when they're consistent and when they're not. So in order to solve this equation here, we'd multiply the second equation by 4, and we'd end up with 3x plus 2y is 5. Sorry, we multiply this one by 2, we get 4x minus 2y equals 16. And then when we add those together, we get 7x is 21, so x is 3, and y is minus 2. So this corresponds to this situation here. Now, this equation here, we're going to multiply the first equation by 2, so we get 8x minus 6y equals 4. At the second one, we leave the same. 8x minus 6y is equal to 4. We subtract them, we get 0 equals 0. Now, if you get something like this, this tells you that the 2 lines are the same line. So this is a consistent set of equations. And if we look, we can see that one line is just 2 times the other line. So this is this situation here. So these equations are consistent. And if I wanted any solution, I could choose any point on this line, will be on this line as well. When I come to solve this one, I'm going to multiply the first equation by 2. So I get 6x minus 2y equals 6. And then I've got minus 6x plus 2y equals 1. And when I add those together, I get 0, here, 0 plus 0 equals 7, exclamation mark. That cannot be true. So these are inconsistent. And this represents 2 parallel lines. Okay, so that's what can happen in 2 dimensions. Now, in 3 dimensions, we've got some different options. In 3 dimensions, ax plus by plus cz equals d represents a plane. And when we do more work on vectors, we will understand this a bit better. So this, if I had 6x plus 2y plus z equals 10, that is a plane in 3 dimensions. So if I've got a system of 3 simultaneous equations, that can represent the intersection of 3 planes. And the system is consistent if there is at least one solution. Now, just because it's difficult to draw live on the visualizer, I've prepared this in advance. So these are the different things that can happen with planes. If I've got 3 planes, you could have a unique solution. So you could have one plane here. So this is the first plane, the second plane opening like a book, and then the third plane slicing through. And that point there is on all 3 planes. So that has a unique solution. You could have this situation, which is called a prism. So we've got one plane along the bottom, we've got a sloping plane and another sloping plane. Now these, there's no point that's common to all 3 planes. They are not consistent because there are no solutions to that. We could have them intersecting like this. So when they intersect like this, they form what's called a sheaf. And it's like a hay bale, old-fashioned hay bale. This line here is common to all 3 planes. And so any points on this line will be on all the planes. So there's not a unique solution, but there are solutions to this. So this is a consistent set of equations. We could have 2 or more planes that are parallel. So we could have these 2 planes as parallel and this one going across it. Then there will be no solutions. And the equations are not consistent. In order to see if one plane is parallel to another in 3 dimensions, if you had x plus 2y plus 3z equals 10. If you have anything that's a multiple of the coefficients of x, y, and z, that will be parallel. So if I had something like 10x plus 20y plus 30z equals -4, these two planes would be parallel planes. You could have planes that coincide. So you could have two planes that are the same and one cuts them. And this would be a consistent set of equations because you will have a line that is on all of them. They could all three be the same one. These two examples don't come up very often at all, nor does this one. The main examples you need to know are the prism and the sheaf and intersecting at a point. So in the next video, we will look at how you determine which of those things is going on.